All right, in my last lecture, I showed how to set up a free body diagram for the hanging mass and how to identify the equal and opposite forces for each of the forces appearing in the free body diagram. So remember, the idea is we talked about this mass, we drew a dot representing the mass, we had a force F sub s, that is this vertical shaft pulling the mass to the right using the spring, and the equal and opposite force would be the force of this mass pulling on the shaft using the spring. So I called those Fs and Fs prime. There was another force, the force of this bar up here pulling up on the mass. I think I called that force 1. And then the equal and opposite force in the sense of Newton's third law is the mass pulling down on the bar using that spring. There's another force. This was the force of this scale. It's been redirected using the pulley. The force of the scale pulling the mass to the left using the string. And then the equal and opposite force would be the force of this mass pulling up on the scale using the string. I'll call it F2 prime. And then we have the earth pulling down on the mass using gravity. And then I'll draw a dot representing the earth. We have this mass pulling up on the earth using gravity. And it looks like I accidentally called this prime, so let me erase that really quick so I don't confuse anyone. This is not, okay, there we go. All right, so those are the equal and opposite forces. One way, by the way, to see if you are correctly identifying equal and opposite forces is if you get rid of that force, then if you get rid of a force, its equal and opposite force should go away. So for example, let's suppose you incorrectly identified F sub s and F2 as equal and opposite forces. As I mentioned before, they do happen to be equal in size and opposite in direction, but they're not the equal and opposite forces that Newton talks about. So let's say you mistakenly said, oh, Fs and F2 are equal and opposite forces. Well, what you could do is you could imagine cutting this string right here. You could do that, right? So you could cut the string, and if you cut that string, what would happen? If you cut that string, then this force goes away, right? So that force would go away, that force would go away. And what happens? Well, if you cut the string, that goes away. Does this force right here, the force of the spring, go away? No, you can have that spring force still pulling on it, but now that would be an unbalanced force and would cause this mass to accelerate to the right, which is exactly what would happen. You cut the string and this gets accelerated to the right, and so this force does not go away. If we misidentified that force 2 that I just erased with this as being equal and opposite forces, I would erase that. I would have to erase that too, right? But that doesn't go away. So those are not equal and opposite forces in the sense of Newton's third law. Okay, so let me redraw that force here. So we had 4 forces acting on this mass. That's the equal and opposite force right there, F2 prime. Now, what I want to do is I want to talk about this mass that was spinning around. So I've taken a screenshot of this mass right here. This is when we're spinning it around and the spring is stretching, and we want to draw a free body diagram for this, okay? So I'm going to draw a dot here. This represents this mass, and let's identify the forces acting on it. Okay, so let's start, well, there's still gravity, right? So there's the force of gravity pulling down on it. You might say the earth is pulling down on that mass using gravity. And then we would still have an equal and opposite force. I'll have a dot right here. This represents that mass pulling up on the earth using gravity. Okay. What else do we have? We have this bar pulling up on it. Well, we called this F1 before, we'll call it F1 again. And then, of course, the bar, this mass is pulling down on the bar right here. We'll call this F1 prime, okay? And then we have the spring, like this, F sub s, this spring pulling it to the right. And then we've got over here, we've got equal and opposite force. We've got the mass pulling outward on the vertical shaft using the spring, right? Notice that there is no longer another force pulling it this way. There are only 3 forces acting on this mass because we don't have a string attached to it pulling it like this. So we have 3 forces pulling on it. So notice, whereas in here we have 4 forces acting on the mass. In this case, here we only have 3 forces acting on the mass. In this case, right? These 3 forces right here, F1, Fs, and Fg, are the 3 forces that are acting on this mass. Okay? Now notice, just like before, Fg and F1 are going to be equal to each other. So F1 is equal to Fg. That is not, oops, I said G. They're equal to each other not because they're equal and opposite forces in the sense of Newton's third law, right? But they are equal to each other because this mass is not accelerating up or down. So the acceleration, this is by Newton's second law, we know that F1 is equal to Fg, right? Because if they weren't equal to each other, this thing would be accelerating up or accelerating down. And that's exactly what would happen if we were to cut this string up here. F1 would go away, there'd still be this Fg aiming down, and the mass would fall downward. Okay, now what about this one right here? Well, we have F sub s is pulling this way. There's no other force pulling out. So F sub s is an unbalanced force. Unbalanced. In the sense that this mass right here, there's not another force pulling it to balance that. And because F sub s is unbalanced, that means that this mass right here has to be accelerating in the direction of that force. So by Newton's second law, the mass is accelerating in the direction of F sub s. Okay, that force, F sub s, is providing what is called a centripetal force. It's a force pulling it toward the center of its orbit. So let me draw a top view of this. If I were to draw the top view, here would be this vertical shaft, here would be the spring right here, and here would be our mass. Okay, it's going around in this orbit like this, and the spring is pulling it inward like this. You know what I should have done is drawn this in different colors. So let me erase this and redraw with different colors just so. Okay, so here is the shaft. Here is our hanging mass. There's a spring attaching them. And now I'm going to draw the force, this unbalanced force acting inward. That's the spring pulling it inward, right? So the spring is pulling it inward like this, and that is what is causing it to go in this circle. If you were to cut this spring right here, that force would go away, and the mass would just fly in a straight line in a tangential direction. But what's happening is the spring force is keeping it from flying in a straight line. It's keeping it moving in a circle. That's what F sub s is doing. So F sub s is what's called a centripetal force. Centripetal force. That is a force that attempts to move something in a circle. So I'm going to stop there and talk a little bit more about that in my next lecture.